Welcome back. In this segment, we are going to talk about lighting. And there's a little bit of a relationship to the shadow analysis. But here, instead of looking at cast and attached shadows, we are going to look explicitly at the pattern of lighting on objects and try to reason about the location of the light source. So in many ways, this adds a nice additional tool to the shadow, both cast and attached shadow analysis that we've already talked about. By way of motivation, let me talk about this photo right here. Some of you may remember this. This is Kim Jong-il. For a while, it had been rumored that he may have been deceased, hadn't been seen in public in a long time, and there was speculation as to the turnover of power to his son. And during the sort of peak of that speculation, this photo was released. And I'm going to just highlight here the leader from North Korea and explain why there were some questions as to the authenticity of this photo. So what you can see here is clearly an outdoor photo. You see the North Korean leader there in the middle. And what you notice is a couple of things. So notice this little black line right here. It actually extends on the other side of the soldier to the leader's left. And you notice that line, that little thin black line right there, seems to discontinue behind the leader. That's sort of weird. Why is that? Was he digitally inserted there and they forgot to put the line in? You also notice the shadow that the two men on either side of the leader are casting. Pretty thick shadow, cast shadow onto that surface. But look at the leader's shadow. It's a little bit thinner. It seems to be almost, well, not quite the right size. Now, we've already studied cast shadows. We've already studied how the human visual system can reason and can't reason about these. It's not immediately obvious that a cast shadow analysis will help here. Why? Well, because basically everything is a half-plane constraint. And all those half-plane constraints are going to say that the shadow lies over here. There's a couple of distinct shadows in the back here, but it's hard to really find probably enough here to get us a good localization of the light. Now, obviously, in addition to those, so those are two things that sort of give us a little bit of doubt. Now, there's other patterns of lighting. So, for example, you see that the North Korean leader's this side of his body is illuminated, this side is not illuminated. You see a pattern of lighting on his face. This side of the face is bright, this side is darker, and maybe we can use that pattern of lighting to reason about the lighting in that scene and determine if they are consistent or not. And that's what we're going to be talking about here. And at the very end of the segment, I'll come back to that photo and show you an analysis that we've performed on that. All right, so let's start with the general model of lighting. So this is a simple 3D rendering. And from this pattern of lighting that you see here, and of course the cast shadow, you've got an indication that the light is somewhere up and in this direction. Why? Well, the shadow tells you that because of the orientation of the shadow. But also you can see that the illumination pattern, the top of the ball, the top right part of the ball is illuminated, the bottom side is not illuminated. So clearly the orientation of the light is here, and it's intuitive. But you also see this gradation. You see this gradient of the fall off of light. It's very bright at the tip here, and it sort of falls off. And we want to be able to describe that pattern of illumination as a function of two things. Well, where the light is, obviously, and the geometry of the scene. What is the shape of the object being illuminated? So obviously we want to do all of this in 3D, but what I'm going to do is I'm going to do this whole lighting segment in 2D. We're going to live in flat land for a little while. We're going to go through the whole generative model, we're going to go through the whole estimation, and then I'm going to extend everything to 3D, and you're going to see that things extend actually very, very nicely. So we can stay simple in 2D for a little while. So let me just describe my 2D world now. So instead of a sphere, I have a circle. And I have a light source that is in the same plane as the circle. So think of my whole world living on the top of a table. I have an object, which is a circle. I have a light somewhere in the plane that is illuminating it. This part of the circle will be illuminated. This part down here will be in shadow. Okay? So let me just define a little notation that we're going to need. L is pick a point on the, I've drawn, by the way, the light source locally here just so you can see it. We're eventually going to push this out to infinity, but I want you to see what I'm talking about. Let L be a 2 vector, we're in flat land, that for a particular point on the object points to where the light is. And let N be the surface normal 2D vector of the object. And by surface normal, I simply mean take a point on the object, draw a tangent to the circle, and that little vector is perpendicular to the tangent at that point on the object. Both of these obviously have a correlate in 3D. We'll do that when we go to 3D. Okay? So, for example, here, now the light direction and the surface normal are aligned, and here the light direction is down here, and now you can see that I'm in shadow. So when the light direction does not have a clear view because it's occluded by the object, this obviously is, this point right here will be in shadow. So when the light is plus or minus 90 degrees relative to the surface normal, I will be illuminated by differing amounts. We'll see that in a little bit. And then for everything underneath, I will be in shadow, and only the ambient term will contribute to the lighting. All right, so let's go back to where we were before. I've got a 2D surface normal. I have a 2D light direction. And again, just so you can see it, I'm going to leave the light locally here. Eventually, we're going to assume that that's at infinity like the sun, but I wanted you to be able to see it so you always remember what that light is right there. All right, let me write a generative model for the pattern of illumination on an object given these two terms and a few more things. Now, I'm going to assume a few things. I'm going to assume that the light is infinity. I'm going to assume that this is a so-called Lambertian surface. What is a Lambertian surface? It simply means that it reflects light evenly in all directions. So think of it as a matte surface, a non-shiny surface. When light hits it, light bounces out with equal illumination in all directions. That's a Lambertian surface. And just for simplicity now, I'm going to assume it's the same color or reflectance across the whole object. Okay, so infinite light source, Lambertian surface, constant albedo, constant reflectance, constant color. Okay, so pick a point on that surface that I just constrained. I have a surface normal, which is the tangent vector, which is the normal vector to the tangent, and I have another vector, these are both 2D vectors, to the light direction. Now, the brightness at that point is, under those assumptions, is equal to, well, the color of the surface, that's the surface color, so black, it's going to be dark, white, it's going to be white, times the dot product of the surface normal and the light direction. So notice here, these are both, of course, column vectors by convention, so I'm going to make that a row vector. I'm going to take a dot product between those two. We'll talk about that in a little bit more in a little bit, because that's the important part here. So that's just a scalar value, plus an overall ambient light, which is just what happens when this light over here bounces around all the surfaces and eventually comes in and contributes to a little bit of light right there that is non-directional. Okay, so under the assumption of brightness, a Lambertian surface, constant reflectance, infinite light source, I can describe a model of the brightness here as a function of the geometry of the object and the geometry of the light, the color of the object, and just this additive term here, which is the ambient light. All right, let me write this out a little bit in terms of the vector, because this is sort of the important part that we should really understand. So again, we're in flat land, so n is a 2 vector, nx, ny. L is a 2 vector, lx, ly. By the way, where are we going with all of this? Well, eventually we'd like to understand the lighting in the environment. We want to understand this, and we maybe want to understand that, and we want to be able to make, and we have this measurement, and I'm not sure where this is going to come from yet, but we'll figure that out later. But basically what we're trying to do is write a model for the pattern of illumination on an object, and then we're going to try to reason about the light direction and perhaps ambient term. All right, so this is a scalar value r. This is a scalar value a. I've got a 2 vector, I've got a 2 vector, and let me just write in the dot or inner product. So it's the x component of the surface normal times the x component of light direction plus the y component of the surface normal times the y component of the light direction. Let me remind you, because this is good by way of intuition to understand why is there a dot product here between these two vectors, that the dot product of two vectors is equal to the cosine of the angle between them. So there's that angle between the vectors, divided by the vector length of each vector. So let's, for simplicity, assume these are both unit vectors. Then the dot product is just the cosine of the angle between them. All right, let's see if this makes sense. Okay, so this blue curve here is the cosine as a function of angle 0 to 2 pi. So when the angle between the vectors is 0, the cosine is maximal, 1. When I go to pi over 2, I am minimal at 0. Of course, at minus pi over 2, I'm at 0. It goes negative for a while, and then it goes positive again. All right, let's see what's going on here. So what does it mean for this the angle between the light direction and the normal to be 0? It means they're lined up. Okay, when they're lined up, this equation and this graph right here of cosine tells me I get the maximal amount of light. Sure, if the light is right here, coming down right from the top, I'm going to be brightest here, and I'm going to start to get darker and darker and darker as a function of cosine, by the way, until I get to minus 90 and 90, at which point the directional light will not contribute, because I'll be at 0. Now something weird happens with the cosine, by the way. It goes negative. Well, I can't have negative light. So this equation is a little bit of a cheat. This equation only works when you are plus or minus 90 degrees to the light source. Otherwise, you have to do a half-wave corrected cosine. That is, all the negative values have to go to 0. So for now, we'll always assume that we're analyzing parts of the surface that are within plus or minus 90 degrees relative to this. We are brightest here, and we are darkest here. By the way, that equation right there is why it is cold in the winter and warm in the summer. In the summer, the light is almost directly above us. The surface normal of us on the Earth and the light are almost perfectly aligned. We get maximal light. In the winter, the sun is lower on the horizon, so the angle it makes with the Earth is greater, less light. This is the exact equation for change in temperature as a function of the seasons, and also, by the way, describes the pattern of light on a surface with certain assumptions. The light is infinitely far away, Lambertian, and constant reflectance. By the way, why did I assume constant reflectance? Well, just because I wanted to have only one term right there. I just didn't want to muss it up. Okay, so again, what are we trying to do? We're trying to reason about the lighting, directional and ambient, from, well, we're going to make some measurements of the appearance, and maybe we know something about the geometry. So what do I know? Well, what do I not know? I probably don't know the color of the surface. I certainly don't know the light direction, and I certainly don't know the ambient term. So those are the things I'm trying to figure out. I certainly know this, the brightness. And let's just go ahead and assume that we can figure out the geometry of the object we're analyzing. Because if we can't, we're sort of in a world of hurt. Because I know this one thing, and I don't know anything on the right-hand side. And at that point, I may as well go home. So let's assume we're going to be able to infer geometry of objects being analyzed. And of course, we can measure the brightness, because that's easy. We actually have the brightness. Okay, so that doesn't seem too bad. I mean, we have a few more unknowns here than we have knowns, but it's not really out of whack. Now, one thing that's troubling me looking at this equation is that this unknown is multiplying that unknown. And that's never a good thing, because that's going to lead to a nonlinearity in our estimation. So I'd like to fix that. This I can deal with, because this is an unknown being added to this. This is a known scalar vector being multiplied by an unknown vector. But this thing is causing me trouble. Now, but here's the thing. You remember I told you I'm going to go ahead and assume that the light direction is at infinity. And sorry, that the light is in infinity. And if the light is in infinity, all I care about is the orientation of the light. Yeah, I can treat this as a unit vector, right? I don't care how long this vector is. Well, if all I care about is asking what is the direction to the light, and I don't care about the magnitude of that, well, can we agree that I can take this scalar value, which is constant across the surface per my assumption, and just say, well, all it's going to do is multiply the length of that vector, but not the orientation, in which case I can go ahead and just ignore it and assume I'm going to estimate a unit length vector. And that's exactly what I'm going to do. I'm going to go ahead and assume that the light is infinity. I'm going to go ahead and assume I don't care about the magnitude of that. I'm only going to estimate the orientation. And now I've got a nice clean looking equation. I've got the brightness, which I can measure as known. I've got the surface normal. That's not immediately obvious how we figure that out, by the way, but we'll get back to that in a little bit. But let's assume we can know it. Now I've got three unknowns, two components of the light direction and ambient term, and I have for each of these measurements that I can make. Obviously, I can make measurements all along the surface here, and now I've got a linear system of equations. So this system is linear in three unknowns, Lx, Ly, and the ambient term. Okay, good. That's starting to look good. I'm starting to feel good about this. So let's see. I've got three unknowns. Well, let's make three measurements. So here's a point on the surface. Here's a point on the surface. Here's a point on the surface. Notice a few things. the brightness at these will change. Of course they will. The light is somewhere over here. Let's say it's going to be brightest when, well, it looks like it's going to be brightest somewhere along here where the angle relative to this is 0, and then it's going to get darker as I move away. So the different brightness, different brightness, different brightness. Surface normal, surface normal, surface normal. By the way, in flatland, surface normals are easy because I'm in flatland. So I compute the tangent, I compute the normal, I'm home. So there's no problem with computing the normals here. I'm just thinking downstream when we go to 3D, but let's worry about that problem when we have to. So now what I can write is that the intensity at position I, that's what the subscript is there for, is equal to the normal at position I, that's that right there, dotted with L, single L, everything's at infinity, those three vectors are parallel, plus a single ambient term. So I'm indexing on the thing that I'm making multiple measurements from, and I have a fixed light direction and a fixed ambient term. All right, well, let's write this out and start to figure out how to solve this. So let's write out the dot product. So it's nx, lx, ny, ly, and of course the x and the y are indexed on I because n is indexed on I. Okay, there is one constraint that is linear in lx, ly, and a because those unknowns are only being multiplied by scalar values, which of course I know. All right, let's make 3 measurements. Okay, and why am I making 3 measurements? Well, I have 3 unknowns, L and A. We'll get to later on what you do when you have more than 3 measurements. So here's 3 measurements, B1, B2, B3. Lx, of course, is the same, Ly is the same, A is the same. All right, let's get this into matrix vector form because we're going to obviously solve the simultaneous linear equations. I pack in my 3 measured brightnesses here, B1, B2, B3. I create 2 vectors with the x and the y component of the surface normal. Those are multiplying Lx. These are multiplying Ly. And I have an ambient term, which is just multiplying a constant. So what did I do here, by the way? I just took these 3 linear equations, and I looked down the columns. So nx1, nx2, nx3, that's one vector. ny1, ny2, ny3, that's another vector. That vector and that vector are correspondingly being multiplied by Lx and Ly, scalar multiplication times a vector, and that's equal to the unknown A, which I've pulled out, times 1, 1, 1, because there's nothing multiplying here. And that's, of course, equal to the vector b1, b2, b3. I now have that in linear algebraic form. Again, this is the model, unpacked in terms of the dot product, written out in vector form. And now let's just pack it into a matrix. So what am I going to do here? This vector stays the same. I'm going to take this vector, and that vector, and pack them into the columns of a matrix. I'm going to left multiply it by my unknown Lx, Lya, Lx, Lya. So it's B1 is equal to nx1, Lx, ny1, Ly plus A, and so on and so forth. So I've simply taken this equation, written in vector form, into matrix form. Why did I do that? Well, now I'm sort of home. Why? What am I trying to do? I'm trying to estimate Lx, Lya. That's the lighting, both the direction and the ambient term. I've got a 3 by 3 matrix here. If I assume that matrix is invertible, well then I'm home. I've got a vector times a matrix big N times an unknown U. I simply left multiply by n inverse, again, assuming the determinant of this is non-zero, that it is in fact invertible. I now have the identity here, and I have my solution U, the first 2 components of which are the light direction. The third component, which is the ambient term, is equal to n inverse B. So pack in the normals for 3 points, pack in the values of the brightness there, invert the matrix, and you will estimate the 2 components of the light direction plus, to boot, the ambient term. Good. Super easy to do. Obviously, we want to be able to do this from more than 3 measurements. There's no reason to stop there. But let's go to 3D, and then we'll worry about what we do when we have more constraints than unknowns. All right. So 3D. Good news is everything works. The equation is exactly the same. The brightness at some point on a sphere now, 3D object, is equal to the 3D surface normal dotted with inner product, the light direction, which is now a 3 vector, plus a scalar ambient term. The model holds. I'm still assuming Lambertian. I'm still assuming a constant reflectance across the object. I'm still assuming that the light is infinitely far away. And I'm still assuming I'm only looking at things plus or minus 90 degrees relative to the light source because of the negative component of the cosine for that dot product. So that's the good news. Okay, let's see what happens. What is a surface normal? Nx, Ny, and z. It's a 3-vector. What's the light direction? Lx, Ly, Lz. Now, let me just pause here for a second and ask, well, where am I going to get these from? This is a 3D surface normal. I have a 2D image. Well, if I'm looking at a sphere, this is trivial. I know what the geometry of a sphere is. For everything else, it's not at all obvious. So, here it is. When you are estimating lighting, from the pattern of lighting on a face, for example, we need a 3D model. Now, generally speaking, that's a hard problem, but for faces, fitting 3D faces to images is getting really, really good, and I'll show you an example of that when we do the photo of the North Korean photo from the very beginning of the segment. But this is the catch, is you need 3D geometry, you need 3D models in order to estimate 3D lighting. Okay, with that assumption, let's keep going. All right, let me write out the dot product. I've got Nx Lx plus Ny Ly plus Nz Lz. So the brightness is equal to that dot product plus an ambient term. This is now linear in 4 unknowns. Lx, Ly, Lz are all being multiplied by something I know plus an additive term. So in 3 space, I have 4 unknowns. 3 vector for light direction, 1 for ambient term. I have 1 measurement. If I can make 3 more measurements, I have a fully constrained system of linear equations. So this is, you can see it's the same game. What changed? This column right here. I just need the z component of the surface normal. I get the z component of the light direction. Everything is exactly the same. So let me just go ahead and turn the crank here. I'm going to take that equation. Here are my b's. Here are my x, y, and z components of the surface normal, multiplying Lx, Ly, Lz, and a. So that is my vector formulation of the linear system. Let's go ahead and put that in matrix form. Here are my 4 b's. Here are my 4 surface normals. Here's my 4 unknowns, Lx, Ly, Lz, and a. I now have a 4 by 4 matrix. Again, assuming that this is invertible, that the determinant is not 0, I can solve trivially. B is equal to nu, left multiplied by n inverse, and I get my unknown u, which is just n inverse b. I unpack the first 3 components. I have my 3D light direction. Straightforward. And you can see very natural extension from 2D. I just did the 2D first because it's a little bit notationally simpler. Now, so how do I solve this in practice? Pick 4 points on an object. Tell me what their brightnesses are. Tell me what their surface normals are. I need a 3D model to do that, and do that. Now, obviously, in an image like this, why would I stop with only 4 measurements? That's all I need. But you and I both know that there's noise in the system, there's compression artifacts, there's a little bit of uncertainty in measuring brightness and surface normal, and so there's no reason to stop with 4. We should make more measurements. Well, how do we do that? Well, now we need an over-constrained system of linear equations. So I have 4 unknowns, Lx, Ly, Lz, a, but I can pack in as many rows in here as I want. So what is this? These are my brightnesses. Pick a point on this sphere over here. These are the corresponding surface normals from the point at which you've extracted a brightness. Pack in as many rows as you want. I've packed in a little n of them, 10, 20, 30, 40, as long as it's more than 4, pack them all in. But the problem now is that this is not a square matrix. Yeah, so the reason, the nice thing before was I had vector is equal to square matrix times vector. Square matrix, trivial, invert it, left multiply, done. This is not a square matrix, so now we have to do something a little bit different. We're going to do least squares. Let me just walk you through this very quickly. I still have a vector is equal to a non-square matrix times u, so I can't simply invert that matrix. So what am I going to do? I now have to do a least squares estimation. So I'm going to write a quadratic error function in the unknown u, which of course is my 4 lighting parameters, which I want to minimize. I want to find the u such that when I multiply n by it and subtract it from b, it is minimal. I'm going to make that quadratic because that's easy to solve in closed form. I'm going to differentiate this. This is a paraboloid, of course. I'm going to differentiate that with respect to u. That's 2 n transpose times nu minus b. That's just the polynomial expansion here of the derivative. The 2, by the way, set that equal to 0, set equal to, solve for u. 2 goes away because of the multiplication by 0. And now I have n transpose nu minus n transpose b, or n transpose nu is equal to and transpose B. This, of course, is the unknown. That's known. This now is a square matrix. N was a tall, skinny matrix. This is a short, fat matrix. I multiply those, I got a square matrix. So now U is equal to that thing inverted, N transpose N inverse, times N transpose B. That, of course, is just the least squares. So all I did here is derive least squares for you. So that's the least squares solution. Everything works just as well. I've just made a whole bunch of measurements. So the only rub in this analysis, actually there's a couple of them. The assumptions, you have to assume reasonably Lambertian surface and constant reflectance, constant color, infinite light source. That's not so bad outdoors. But where do you get the 3D model from? That's where this technique is challenging. And now let's talk about its application. So faces is a long history of studying these, particularly in computer vision. And we actually have pretty good models for faces these days. And we have pretty good techniques for fitting faces directly to a single image or a pair of images. I won't talk about those techniques, but they're fairly well established. And you can find lots of literature on that. So if I have a single face like this, we can actually fit 3D models to that pretty well. And once I have a 3D model, I've got 3D surface normals because that's what a 3D model is. And now all I have to do is constrain that 3D model to be on parts of the face with what? Constant reflectance. Be careful with beards and mustaches and scars and birthmarks like the one I have over here. So we trim the model to get rid of the eyes and the nose and the lips because those have different color. For every patch that you see there, I get a 3D surface normal. I also get the underlying intensity underneath that patch. And now I build that matrix N, I build that vector B, use my least square solution, and I am home. Okay, let's go back to our fearless leader of North Korea. And the question is the lighting in here consistent across everybody that you see here? So let's take the 4 people up top, the 3 people on the bottom. We're going to build 3D models for each of the faces. We're going to extract surface normals, we're going to extract brightness, and we're going to estimate the direction to the light source because, again, something looks a little funny down there with those shadows. Okay, so for the fearless leader, what we did is we built a customized 3D model where we used multiple images, and you can see we've done a pretty good job of capturing his geometry. Here's a tessellated surface overlaid. You can see it's pretty low resolution, by the way, but we have a lot of measurements. So once we overlay the model for every point here and here and here and on the nose, but not the mouth, not the eyes, not the glasses, obviously, we get a measurement. And we do the same process for each of the 7 people you see here. And the way I'm going to visualize the results here is I'm going to render a sphere illuminated by the estimated light direction. And you can see that they're all basically in the same lighting environment. The light is off and to each individual's left side. And so, in fact, the lighting here seem to be consistent. The problem down below, by the way, with that thin black line was that behind the North Korean leader was a door to a stairwell up into the stadium. That's why there was no line there. And I think what was happening was that he was stepped forward just a little bit relative to the 2 people on either side. And that caused his shadow to be cast a little bit shorter because he's further away from the surface. So again, another indication that looking at shadows can be very, very deceptive. But you can see now that we can analyze the pattern of lighting on, for example, a face. Or now this jacket would be hard because it's black, so there's probably not going to be a lot of pattern. But like a fixed color shirt that's not too dark, you can analyze. I like faces quite a bit because as the light is, for example, over here, this is going to be bright, this is going to be dark. When the light is over here, this will be bright, this will be dark. When it's above, this will be brighter and this will be darker. So faces are really good. They have a relatively complex 3D geometry. Good, because I have lots of surface normals that I can estimate from, particularly around the nose here, from one side to the other. But it's also a fairly well understood 3D geometry to the extent that I can build 3D models from a single image, fit them to the image, extract out the 3D normals, extract out the brightnesses. Now I should mention with Kimo Johnson, we had one small paper where we showed that if you just analyze the boundary of an object, you can essentially do that 2D solution that I showed you. I don't necessarily recommend that because that had to make some other assumptions that are a little tough, that are a little constraining, particularly if you combine this analysis with the shadow analysis, and I don't recommend it. So I recommend this lighting analysis when you can build 3D models, either of faces or objects of known geometry, a mailbox, a fire hydrant, things out in the world, a car. Well, a car's not a good idea because it's probably not a matte surface. So remember, matte surface, constant color, known 3D geometry. You can then reason about the 3D position of the lighting. It's a very powerful forensic tool, particularly in combination with the cast, attach shadows, and occasionally the lens flare. Okay, that's it for this segment. We'll pick it up in a little bit when we come up to the next one. See you soon.